Let us take a look at the next classification algorithm named knife Bayes algorithm. This is the algorithm that uses the same logic of the classification, starting with the training dataset, build up some model, and then when the unknown testing dataset comes in, you can use the model to make the prediction. It is also a category of white box classification, indicating that you can understand how does the prediction are made. So let us learn what is a knife Bayes. Knife Bayes is based on a statistical classifier concept. So it uses probabilities to make the predictions. And the foundation is based on Bayesian's theory, and the performance is actually pretty well. Personally, I use knife Bayes a lot in my research. Not only it can make good predictions, but also you can understand how does the how does the prediction be made, so that you can use that model to learn the concept or knowledge from the training data set. And therefore, personally, I like this algorithm a lot. So let's use an example to learn what is a knife Bayes algorithm based on the probability. In this case, we use the same data set as we introduced in our previous video, indicating that we want to use age, income, student status, credit rating to predict a person is going to buy a computer or not. So you can see that there are actually two classes for us to make the prediction. Either this person is going to buy a computer or not going to buy a computer. And you can see that this whole thing is our training data set. So we have about 14 different individuals for us to train the information from this set of the data, and then saying that we have unknown data coming in. So this is our next customer just registered in our website. And we want to see, do we want to recommend this person to buy a computer or not? And therefore, we want to take a look of this data over here. This person's age is less or equal to 30 years old, income equals to medium, that person is a student, and the credit rating is fair. So based on this information, we want to make our predictions using the knowledge that we extracted from our training data set. And let us learn how is knife Bayes trying to do this. So Bayesian theory, let X be the data sample indicating the unknown data set comes in. So this is our example based on the data that we gathered. We want to predict whether this person is going to buy a computer or not. So that is our target. And now let H be the hypothesis, so indicating that this person, we have two hypotheses because we have two labels. One is buying a computer, the other one is not buying a computer. So we're saying that we can make two hypotheses. One hypothesis is that this X is going to buy a computer. The other hypothesis is that this person is not going to buy a computer. So those are the two hypotheses that we can form. And basically, we want to compare the probability of the two hypotheses. The one has a higher probability is the one that we make our prediction. And therefore, classification is to determine based on this X situation. So this is our customer. We want to predict whether or not he's going to buy a computer or not going to buy a computer. So the probability that hypothesis holds given the observation data sample on X. So this is exactly what we mentioned. Customer will buy a computer given that known customer's age and income. And basically, we want to learn through the knife Bayes, how do we calculate this value here? And therefore, in Bayesian theory, it's very straightforward. Given a training data X, posterior probability of hypothesis H, so basically P of H under the condition of X, which is the value that we want to calculate it, equals to this value multiply the probability of the hypothesis that we are making divided by the probability of this sample that we see. So in next slide, we try to explain one by one. P of H, which is prior probability, which is the initial probability for the hypothesis that you are making. In other words, if your hypothesis is saying that this person is going to buy a computer, P of H is the probability of buying a computer. In our example, there are 9 out of 14 people is buying a computer, so the probability of buying a computer is 9 divided by 14. In other words, if the hypothesis is that this person is not going to buy a computer, then we have 5 out of 14. That is the probability of not buying a computer. So we can handle 1 values already. P of X indicating the probability that the sample data is observed. So basically, it comes in here. What is the probability that the sample data is being observed? In our naive Bayes theory, 2 slides later, you will see that this is actually not important because we are comparing the probability of buying a computer versus probability of not buying a computer. They all divided by the same situation over here, P of X, and therefore P of X is not important in this naive Bayes theory. Now, the most important thing is going to be in here. So this is Px under the H condition. So based on the hypothesis that we are seeing, so if a hypothesis again is buying a computer, we want to see that based on this condition, what is the X occurred in this condition? That's what we call a posterior probability. So the probability of observing the sample X given the hypothesis holds. So that's saying given the X will be a computer, the probability of X is 31, 40, medium income, etc. And we can see example pretty straightforward. We basically, since X in our example has 4 attributes, we need to separate those 4 attributes and discuss of those things one by one to see that for age less or equal to 30, how many cases of age less or equal to 30 in our training data set holds under the condition that they will buy a computer? So that is how we will be able to calculate that. And we want to do that one by one for 4 attributes in the example. So in your training data set, if you have 100 attributes, then you need to deal with that one by one based on the conditions that X showed to discuss one by one. So let D be the training data set of tuples and their associated classes labels, and each tuple is represented with n attributes, which is what we see over here. That's what I'm talking about. You need to see that those things basically one by one. Suppose there are m classes, so we have number of labels that you need to make the prediction. Then you will, based on the different number of labels that you need to calculate for the probability under the value of X. So that's what I'm saying. Since we in the example we see there are 2 classes, one is buying a computer, the other is not buying a computer, so we need to separate that into 2. One is buying a computer based on the condition of the testing data set, and the other one is buying a computer under the condition of not buying a computer under condition of the testing data. And therefore, we will be able to separate that into 2 of the values, and then basically we want to compare which one has a higher probability. That's why we are saying you need to calculate based on the hypothesis, say buying a computer, and the X saying that we have 4 attributes. We need to calculate that probability for all 4 attributes, multiply them together, and then multiply the probability of buying a computer. And then you need to do that for not buying a computer. And basically, you compare the 2. The one with higher probability is the one that you make the prediction. So that is the basic concept. And of course, we want to see the example. And because of that comparison, you can see that P of X is actually not important because they are divided by the same probability. And therefore, we don't need to bother looking into that probability. So let's take a look at this example, and it will help you understand it perfectly. So starting with the data set, you want to see that in the label you have 2 classes. One is going to buy a computer, the other one is not going to buy a computer. So the very first thing that you need to do is that you need to calculate the probability of buying a computer versus the probability of not buying a computer. In this case, we have 9 yeses in this training data set. So the probability of buying a computer is 9 out of 14, and the probability of not buying a computer is 5 out of 14. And that's why you can see this is going to be the very first thing that you need to calculate it, because you need that probability over here. Next, we want to calculate based on the condition, based on the class. So one is for buying a computer, the other one is not buying a computer, and we want to see the X happening in that situation so that we can calculate this form over here. And now let's take a look at this. Because of the training data set is having the age less or equal to 30, so that is our X for the very first attribute. And in this case, we want to see under the condition of buying a computer, and what is the probability of that is happening over there. So you see that buying computer, there are 9 buying computers, and based on the condition of that, 2 of those are less or equal to 30. On the other side, the probability, there are 5 not buying the computers, and for out of 5 of those training data set, 3 of them are under the age less or equal to 30. So let us double check that to show you the value I represent over here is true. So again, you can see that there are 9 yeses over here. And now we start by looking into the very first attribute, that age less or equal to 30, because this is our testing data set value, so that is our target. Therefore, take a look at this. We're going to see that there are 5 of those age less or equal to 30. Out of those 5, you can see that 3 of them are actually not buying the computer, and then 2 of them are buying the computers. So you can see that there are 2 of them buying the computers. That's where we get 2 cases that buying the computer, and 3 of them are not buying computer. But when we put that into the conditions over here, you can see this. By this attribute, if this is the only attribute that we are cared about, you can see that there are 9 cases that are buying the computer, and 2 of them are in this category. So the probability of that is actually very low, only 22% that contribute age less or equal to 30 who are buying the computer. On the other side, out of 3 of them are not buying the computer, and there's only 5 in our training data set are not buying the computer. So this attribute is actually contribute a lot probabilities in this scenario. So if we only compare these two, you can see that this age less or equal to 30 is actually doing a pretty good job in distinguish whether or not it's going to buy a computer in this case. So that is only the first attribute. The next attribute is income equal to medium. That's again our X situation in the income. So we do the same thing. We try to count. There are 6 of those. They have medium income, and 4 divided by 9 in this case are buying the computers, and 2 divided by 5, because again there are 5 people are not buying the computer, this is 0.4. So you can see that in this attribute wise, buying a computer has slightly higher probability compared with the not buying a computer. So, and now you can see that we have 2 attributes. We want to consider both of them's information together. So later, obviously, we need to multiply all the probabilities together to get a sum of the value. That is how we are able to calculate Px over H condition. And of course, after we calculate all 4 attributes, we still need to multiply the probability of buying a computer or not buying a computer to get the value of the target that we are interested in. So obviously we need to continue working on the next attribute, student, yes, so that's a student, and there are 7 cases of student. 6 out of 9 are actually buying the computers, and 1 out of 5 are not buying the computer. So you can see that the student attribute is have a very strong indication. If this is a student, it's most likely 66% is going to buy a computer. So this one contributes another values into the probability. Finally, credit rating fair. We do the same thing. There are 7 fair ratings. 6 out of 9 is buying a computer, 2 out of 5 represent the probability of not buying a computer, and therefore we can get all of the values that we need, and therefore the next stage is multiply all relevant informations together to make our prediction. So obviously we will need to multiply all the yeses cases together, and then multiply the probability of buying a computer over here and compare that with all of the cases that are not buying the computer, multiply the probability of not buying a computer. So you can see that in here, based on the X situations that we see over here, the PX under the first case buying a computer is this value. And then for the not buying computer is this value. And of course, that's not the end of it because we only handle this element over here, and therefore what we need to do is that we need to multiply the probability of buying a computer and the probability of not buying a computer, and we can get 2 values over here. Of course, the one with higher value is going to be our prediction. This is how the naive Bayes try to make the predictions out of it. And you may be curious why there is a word called naive over here. The idea of the naive is indicating that we simply multiply all the attributes probabilities together without considering there might be some relevancy between the attributes. In other words, we treat all attributes independently, and that's where the naive coming from. So this is how we can make a prediction based on the training data set, and therefore you can see that whatever type of the testing data comes in, we would simply use the probability of the cases and make our predictions over here. So now I want you guys to really understand this, and so I designed a simple assignment for you. This one is probably a little bit more complicated than previous assignments. So let's take a look at this one. Test on the following example and predict if the testing sample will buy a computer or not, and saying that this is the X situation over here. There is a slightly difference over here. We have income equals to low, student yes, credit rating equals to excellent. However, age is slightly different from what we have seen previously. The reason I'm saying that is because now, you see, originally age is been divided into 3 different categories: less or equal to 30, 30 to 40, greater than 40. Now my X have the information of age greater than 30. So obviously you need to do something, some changes over here to fit into the information that has been provided. So this is something pretty interesting I want you guys to think about. And basically I want you guys to make the prediction to see that whether or not this case, this is the next target that we have, this is going to buy a computer or not. I want you to provide me all informations that are needed to do the calculation. So don't just give me a yes or no. This is not a true-false question. This is like an essay question. So I need you to show me all necessary probabilities of how you're calculating that, and then let me know that you really learn how does this naive Bayes try to work. Finally, in the first video, I want you guys to see the comparison of this naive Bayes algorithm versus the decision tree. For decision tree, they actually build up a tree with a flow chart to make all our predictions. So this is the way of the decision tree. For naive Bayes, you will be able to calculate the probability for every single attribute in every single classes. So that is going to provide you the probability of contributions to the predict label. And that is different concepts over here. And this is very interesting for you to understand the differences so that you will be able to know what the difference between the 2 classification algorithms.